Right now, an invisible force is flowing through cities, homes, computers, satellites, and even your own body. It powers lights, moves trains, runs the internet, charges phones, and drives the modern world. This force is electricity. But what actually is electricity? How can something invisible power entire civilizations? Why do tiny particles create lightning storms powerful enough to split the sky? And how does electric energy travel through wires across enormous distances in fractions of a second? In this complete course, you will understand electricity from its most basic foundations to the hidden physics that powers modern technology. We will explore electric charge, electrons, conductors, insulators, static electricity, and the science behind electric energy itself. Because once you understand electricity, you begin to understand the force that powers the modern age.
Electricity is one of the most important discoveries in human history. It powers nearly everything around us: lights, phones, computers, factories, transportation systems, entire cities. Modern civilization itself depends on electricity. And yet, most people never actually see it. Electricity is invisible. You cannot hold it in your hands or watch it flowing directly through a wire, but its effects are everywhere. To understand electricity properly, we must begin with matter itself. Everything in the universe is made of atoms. Inside every atom are tiny particles called protons, neutrons, and electrons. Protons carry positive charge. Electrons carry negative charge. And these electrons are the key to understanding electricity. Normally, atoms contain equal numbers of protons and electrons. This balance keeps matter electrically neutral. But under certain conditions, electrons can move from one atom to another. When electrons begin moving together in a controlled way, electricity is created. In simple terms, electricity is the movement of electric charge. More specifically, electricity usually involves the flow of electrons. Now, imagine billions upon billions of tiny electrons moving through a metal wire. That movement forms electric current. Although each electron is
To truly understand electricity, we must first understand electric charge. Electric charge is one of the most fundamental properties in physics. It exists everywhere in matter. Every atom, every object, and even your own body contains electric charge. Without charge, electricity would not exist. Now, here is the important idea. There are two types of electric charge: positive charge and negative charge. This simple distinction creates some of the most powerful interactions in the universe. Positive and negative charges attract each other, but similar charges repel. Positive repels positive. Negative repels negative. This behavior forms the foundation of electrical forces. Now, let's go deeper inside the atom. Atoms contain positively charged protons inside the nucleus. Around that nucleus move negatively charged electrons. Normally, atoms contain equal numbers of protons and electrons. This balance makes the atom electrically neutral. But sometimes electrons can move from one object to another. When that happens, the balance changes. If an object gains extra electrons, it becomes negatively charged. If it loses electrons, it becomes positively charged. This movement of electrons is one of the most important processes in electricity. Now, imagine rubbing a balloon against your hair. As the surfaces rub together, electrons transfer between the materials.
By now, we understand that electricity depends on moving electric charges. But this creates an important question. If electrons exist inside all matter, why does electricity flow easily through some materials, while other materials block it almost completely? The answer lies in the internal structure of matter itself. Some materials allow electrons to move freely. Others hold electrons tightly in place. This difference creates two major categories: conductors and insulators. Let's begin with conductors. Conductors are materials that allow electric charges to move easily. Inside conductive materials, some electrons are only loosely attached to atoms. These electrons can move freely through the material when an electric force is applied. Because of this freedom of movement, electric current can flow efficiently. Metals are among the best conductors of electricity. Copper, silver, gold, and aluminum are common examples. Copper is especially important because it combines excellent conductivity with lower cost. That is why most electrical wiring around the world uses copper. Now, imagine billions of electrons inside a copper wire. When voltage is applied, the electrons begin moving together through the metal. This organized movement creates electric current. Although individual electrons move extremely slowly, the electrical effect spreads through the wire almost instantly. This is why lights turn on immediately when a switch is pressed. Now, let's move to insulators. Insulators are materials that resist the movement of electric charge. Inside insulators, electrons are tightly bound to atoms. They cannot move freely through the material. As a result, electric current struggles to pass. Common insulators include rubber.
Most of the time, electricity moves continuously through wires and circuits. But sometimes electric charges behave very differently. Instead of flowing steadily, they build up in one place, then suddenly discharge all at once. This phenomenon is called static electricity. Static electricity is one of the oldest electrical effects humans observed. People experienced small electric shocks long before modern science understood what electricity actually was. Even today, nearly everyone has experienced static electricity. Touching a metal doorknob after walking across carpet, removing a sweater and hearing crackling sounds, seeing tiny sparks in darkness. These are all examples of electric charge buildup and discharge. Now, let's understand how static electricity forms. Everything begins with electrons. Inside atoms, electrons can sometimes transfer between materials when surfaces rub together. This process is called frictional charging. Imagine rubbing a balloon against your hair. As the two surfaces contact and separate repeatedly, electrons transfer between them. The balloon may gain extra electrons and become negatively charged. Your hair loses electrons and becomes positively charged. Because opposite charges attract, strands of hair rise toward the balloon. This simple experiment demonstrates one of the most important ideas in electricity. Charges can move between objects. Now, here is something fascinating. The objects themselves are not creating charge from nothing. Charge is conserved. Electrons are simply moving from one material to another. One object gains electrons. The other loses them. This imbalance creates static electric charge. Now, let's discuss why static electricity often remains on surfaces instead of flowing away immediately. Many materials involved in static electricity are insulators. Materials like rubber, plastic, dry air, and fabric do not allow charges to move freely. Because charges cannot easily escape, they accumulate temporarily on surfaces. That buildup can continue until the electrical difference becomes strong enough to create discharge. When discharge finally occurs,